make sure that the project is very clear to everyone, and also to make sure that you, if you have any other questions for the upcoming exam, that we can answer those as well. So I just wanted to talk through the different variables that we have. And you have the temperatures and the relative humidity and dew points. And I want to make sure that you understand what those are. Everybody knows what temperatures are. But notice I have T-def, diff, and T-dev, which are probably bad words for these. Is it called T-diff, just T-average? And what this is we looked at how far every temperature is from the average, and that's what all of these are on each day. So these are actual temperatures, how many degrees you are from the average each day at every point. T-dev is the same thing, except that instead of just how far you are from the average in terms of degrees, these are actually z-scores. So it's kind of like you have different ways of evaluating things. You can either use just the difference from the temperature, or you can use the difference from the temperature divided by the standard deviation that day. And then all of the different days were averaged together to give you the numbers that we have here. So everything that you have here is averaged for, there are like 15 different days. So every one of these numbers is an average of 15 different days at a different location. But the averaging is done differently. One is we're averaging the z-scores as T-dev. The other one is you're just doing a straight average of how far the temperature is from the daily average. And then the same thing for relative humidity and dew point. So does that kind of make sense to people, what these different numbers are? And let me pull up the chat just in case anybody asks there. So if it's clear to everybody that the devs are z-scores and the differences are just the raw numbers, but they're how far you are from the average every day. Now we can look at these other variables. So latitude and longitude, I think it's pretty clear what those are. NDVI is just a measure of vegetation. If it's completely filled with vegetation, it should max out at 1. It never does. It never goes above about 0.9. If it's zero vegetation, it should be not quite zero, a bit above 0, because soil itself will have some NDVI here. But on the whole, this is a good measure of vegetation here. Albedo is a reflectivity. So the higher the albedo, the more it's reflecting. And then this B area frac. This is what fraction of the area is the footprint of buildings. And these are all in roughly 100 meters squares. They're actually 0.001 degrees squares, but it's roughly 100 meter squares. Okay. So that's B area fraction. And then the height, these are the actual heights of the buildings averaged together, and they're the heights in how many stories high they are. And for every building, the number of story, one story is about the same, not totally true, but roughly about the same. So this is the average number of stories within every 100 meters square. Again, elevation, we know. Water fractions, this is how much open water is in every 100 meters square. Okay. So most of them should actually have 0 fractions of water. Oh, like it's not. Okay, there's only 80 of them. Huh. So if they're along the edge, of course, they're going to have, a significant fraction of water if they're near one of the 2 rivers, either the Hudson or the East River. And then most of this is in between. Now, what you want to do is you want to pick one of these variables at a time. You have 6 of these, pick one of these at a time and try to fit them using these other variables. I wouldn't use latitude and longitude for the fitting. So leave latitude and longitude out of your fits, but try these other variables. You may want to do correlations with them one at a time to find which ones have the highest correlations, and maybe start with the highest correlation and then add them in one at a time. And what you're going to find is, as you're looking at how good the fit is, maybe you're looking at the adjusted correlation coefficient or something like that, or maybe F, the F value. You're going to find that they're going to level off. They're never going to perfectly level off, but they're kind of going to level off. And that's when you're going to say, okay, I think I have enough variables here. And then you may want to play around with, which variables you keep in and which ones you leave out, because you want to try to find the best fit. Okay. And the only other advice that maybe I should give you here is you may want to make some of these nonlinear. Like what I did with building height is I said, well, once the buildings get higher and higher, it doesn't matter as much. You can do things like you take a square root, something like that. That's one thing I can recommend. Another thing you can do is, especially with the z values, they're kind of restricted in the range. You may want to kind of divide everything by the standard deviations to get them all into the same range. And then that way, when you make an equation with all the variables, you're going to have coefficients. And some of the coefficients may be very low. So for example, let me just go ahead and pull up building. So for example, you may say that T-diff is equal to, let's call this like, call it like K1 NDV, K1 times NDVI plus K2 times albedo plus K3 times B area fraction plus K4 times building height plus K5 times elevation plus K6 times water frac. Okay, now that's a big long equation, and some of these variables may not be important. You've scaled all of these variables. If you've taken every variable and you've divided by the standard deviation, for example, then the coefficient should tell you how important every variable is, which one contributes the most to giving you the difference in temperature. So then you can go away, you can throw out the ones which don't make a big difference. Okay, now you may find it problematic because water fraction has a whole bunch of zeros, so maybe standard deviation isn't the best thing to use, but you can maybe scale it differently, something like that. Okay, so scaling the variables is pretty useful to figure out which ones are more important and which ones are less important. Another thing you could try, which I did, was, and you heard that in the talk on Tuesday, Sarah did the same thing. She multiplied together height and area fraction to give you a volume. So you can make a separate variable called volume, and maybe you're going to find that that works better. So you can play these games with doing different variables. You can try doing logarithmic, where you do the logarithm of everything. It's all a question of what is going to give you your best fit. Okay? So any questions about any of that? Now you can do everything all together. You can multiply like area times elevation and then take the logarithm of it with all of the other things and so on and so forth. So once you have it set up, and I recommend that you write a a code, right? A program to do this so that you can just keep changing it whenever you have a different idea. Then it's going to be very easy to kind of redo everything. So write yourself, do this as one long program where you kind of set things up at the beginning and then you make variations to it at the end. And then you'll find that it goes pretty fast after that. Okay. So after you do tdiff to tdev, then rhdiff and rhdev and dew point, and you want to decide. Meteorologists tend to use dew point more than relative humidity, and you kind of want to figure out which one fits better, because dew point is more a measure of what is the total amount of water. Relative humidity is the amount of water relative to saturation value, and that can change from day to day. So it's not clear that, relative humidity can be modeled if you don't have the temperature of the day, and therefore dew point might be a better number to use. Okay, so if you get better fits using dew point than you get with relative humidity, then do dew point instead of relative humidity. So you want to decide between the two temperatures, difference or deviation. This is like Z, a straight average or a Z value average. And then you want to decide between relative humidity and dew point. Okay, any questions about that?
Yeah, Professor, I have a question about when we arrange the variables, like changing them. Yeah. So do we have to apply the same thing to all the variables? So like say we decide to log them, then are we supposed to log all the X variables, so NDVI, albedo, and all of them? Or is it like we choose which variables to log and which ones to for example, divide by standard deviation?
Yeah, good question. If you think of, let's say that let's just do two variables here, for example. So let me get rid of some of these here. I'm going to trim this down, or I should just copy and paste. Let's say that we're doing NDVI and elevation. And you may decide that instead I want to do like log of NDVI. Well, let's think about what that means. You could be saying that because of, the leaves are overlapping and stuff like that, maybe logarithm is a better one. You can do that. You can make any types of transformations that you want. It comes down to whatever works best for you. So yes, it's very true that some variables might be better if you take the logarithms, but then you probably want to do the scaling after you've done the transformation. So if you're doing log D NDVI, then you probably want to do log of all the NDVIs and then divide by the standard deviation of the logs of the NDVIs.
Okay, so it's okay to have like NDVI logged and then leaving, for example, elevation not logged, right?
Yeah, it's okay. Now, the thing to think about is NDVI goes between 0 and 1. Elevation can go between, up to anything. So in some cases, you may think, which variable does it make more sense to kind of knock down? If you take the logarithm, the higher numbers become less important in a sense, right? Because 100 becomes 2 and 1,000 becomes 3 and so on. So if you have a variable, you think, well, wait, this has an unlimited upper end. Maybe I want to take the logarithm of that one. And then make things go out to infinity are not as important. Things like that.
Okay, thank you.
So it's basically you're building a model and really anything goes. All that you're trying to do is get the best fit that you can. However, you also want to divide it up. There's 80 points here. You want to hold some of them as test points, as validation points. So the ultimate test is, also which ones will fit your validation points better. And then, of course, you have to do all the same transformations to those. Okay, but don't kill yourself doing this. This is something that people, I mean, in real research, you may spend a few months playing around with this. Don't go crazy on it. Once you do a few things and you think, okay, I got something better, say that you're done. You don't need to go any further. You've made an improvement. Go ahead and stop because you don't have that much time.
Professor, we're trying to be perfectionist.
I know you want to be perfectionist, but there's also realism here. So the realism is, I need you to turn these in Sunday night. So you can't be too perfectionist, and you have other things in your life as well. So do show that you've used an idea and you've made it better, but don't spend hours and hours and hours because you have other things you have to do as well. If you've demonstrated that, oh, I've done this and I understand this concept, that's good enough. Go ahead and write it up. Okay. But scaling is definitely a very good idea. And then playing around with other nonlinear type things, that's something you don't have to do. It's nice if you do it just to see how it affects. But you could spend a lot of time playing around with different variable transformations. Maybe make one that makes an improvement and then pat yourself on the back and say, okay, I've made an improvement, and write it up. Okay. Now, if there's any questions about like the exam on Tuesday, I can answer those as well. If there's anything you'd like to see again, I can talk about things again.
Professor, you mentioned earlier about the setting up a function to run all that rather than typing all them out.
Yeah.
In the R console. Are you able to show us that now?
Sure, I could. Let me get rid of this. Yeah, close it. Okay. So let me get my R back up here. And so we're working with these chick weights again, and we have a bunch of different chicks. So let's see if one thing that you were doing is you were putting out the data from a chick. So you're saying things, let's just say chick 1 is equal to, I'm going